Yeah, so I'm going to be talking about basically this part about scale and precision to some extent. And then also in the second half of my talk, I will be talking about how we apply this to the analysis of insecure uses of cryptography. Yeah, a couple of words about myself. So I'm a professor at Bodden University, and you can see our building here on the right-hand side. So that's where we do foundational research. We work, for instance, on algorithms and data structures for more efficient and precise static analysis. But then I'm also a director at this Fraunhofer Institute here on the left-hand side. And so Fraunhofer is actually a very large applied research organization in Germany and all over Europe. We have about 70 different institutes on a number of different topics. And at our institute here, we are collaborating a lot with companies from the IT sector, but also in mechatronics. And we are trying to aid these companies in applying the methods and technologies that we research. And yeah, so a couple of the tools that you already mentioned, we are already using as a vehicle also to bring some of what we do into practice. So you've mentioned Suit. And if you're using Suit, I can actually tell you we're heavily working on a new major release that we will publish this summer. So that's going to have a brand new architecture, which is going to be a lot more modular and easy to use. But we try to keep all the good bits about Suit. So that should be exciting to many of you. Clodroid, you've already mentioned. CogniCrypt, I will actually talk about a little bit today. So that's our crypto analyzer that we built on top of this latest technology that I will talk about today. And then we also have a framework called Phaser, which is a little bit different from the others because the other three are based on Java technology, and Phaser is based on LLVM. It's implemented in C and C++, and we use it to analyze LLVM IR. And I just heard that some of you are actually working on analyzing x86 machine code. And we've actually also worked towards lifting that machine code towards LLVM IR so that it could be made analyzable with Phaser. We're not quite there yet because that still requires some better pointer analysis, but we are almost there, I would say. So there might actually be some room for potential collaboration. Yeah, like I said, we try to bring some of what we do into industry, and we also have a number of well-known and maybe also not so well-known partners that we work with. So one prominent partner is Amazon. And actually just before COVID hit, we went with a couple of people to New York to meet with Amazon folks there and educate them in the use of Suit and also this CogniCrypt framework that I will explain next. So they're also slowly starting to pick up some of the technology that we build. And that's another really exciting project I can only partially talk about. So what I can tell you, it is with a static analysis security tool vendor, one of the leading ones that you see on the chart on the right-hand side. And it's interesting because this company was heavily invested before in dynamic analysis. So their main products were on dynamic security analysis, and their main selling point was always that dynamic analysis is better because it gives you a better signal to noise ratio, right? So you basically don't have any false positives. Everything that the dynamic analysis finds is a true positive. Yeah, of course, they were missing some coverage, right? Because in a dynamic analysis, you only find things on paths that you actually execute. And so we teamed up with them to actually build a static analyzer that is now part of the product portfolio and which was released actually last year. And what's really interesting now is that since we have this static analysis support now for these different languages, the feedback that they got from their customers is actually that the static analysis is also so good and also has such a low false positive rate that it's getting harder and harder to still sell the unique selling point for dynamic analysis, right? Because now there's something that has good coverage and also has very good signal to noise ratio. So the dynamic analysis is becoming somewhat less important. And that was really nice to see, because these algorithms that I will talk about today, we knew that they worked very well in lab experiments that we did, but now we also have hard evidence that it's also working in the wild, and we're really getting good results also in commercial products. So what I want to talk about today and the rest of this talk is some background about traditional static application security testing. So that's basically the application of static analysis to finding security vulnerabilities. And in industry, it's called SAST. Then I will talk about some algorithmic breakthroughs that some of my PhD students had over the years and that I think are quite important. And then I will show you how we apply this in this crypto checker CogniCrypt that we have developed with some colleagues. And I will also briefly show some results of a large-scale study that we did with this. So if you think about static analysis in theory, it's a really great tool, right? It has a number of benefits. In particular, it works on incomplete code, so you do not even need to have a complete working software product to be able to apply this analysis. You can give immediate feedback to developers, sometimes as the code is being typed. That's really nice. You can cover the entire program, not just a single run, like I just explained earlier. And you can also cover a wide range of vulnerability categories. There are some security vulnerability categories that are hard to find with SAST, but many of them can be found. And you can also often instantly suggest sensible fixes. And that's also something we're making use of right now. But in practice, unfortunately, static analysis has quite some problems, right? So, if, you know, on the previous slide, I showed you that you might think it's the best thing in the world, but in practice, it's not always working that well. If you look at particular some of the older static analyzers, then you will often see results like you see here on the left-hand side. So this is some analyzer applied to some medium-sized project. And what you see here is that you get really tons of warnings, right? So in this project alone, it's more than 4,000 just critical ones and many more supposedly benign vulnerabilities or defects, right? And now if you apply such a tool to your program, of course, most programmers don't really feel like using the tool anymore at all, right? Because now they have to go through all these warning messages. And if you have a bad analyzer, like there used to be a couple of years ago, then you could easily have false positive rates of 70, 80%, right? So most warnings that you see are actually incorrect. And that is obviously a huge detractor to these people's work. So yeah, they're not very happy about having to use these tools traditionally. And many studies actually show that for these reasons, developers also frequently abandon static analysis tools. And you might think, so why is static analysis so hard, right? I mean, in the end, it's just trying to do some pattern recognition of the code. So you want to find some patterns of common vulnerabilities. It cannot really be that hard, right? So let me show you on the next few slides a couple of core challenges that you have to deal with if you really want to analyze real-world programs. And the first major challenge that I also always explain to my students is heap assignments, or so-called aliasing. So for instance, if you're trying to track in a static analyzer whether the secret here that's returned from this method call can actually flow through this print statement here, then looking at this program code, it's obvious that it cannot, right? Because we're printing a different variable. But if we now have such a variable assignment here, then all of a sudden these two names, these two variables are what we call aliased. And then the secret can actually be printed, right? And so this is obviously the most trivial example of aliasing you could think of. But there can be other ones, right? So for instance, this is a nice little program with just 7 lines of code. And you can think about whether there's a possibility that the return value of the source here can actually lead to the sink. And I'll give you a couple of seconds to actually think about this and look into it. So I won't necessarily want you to really solve this, right? And I guess you can in a couple of minutes or so. But what I want you to experience is that although this has only 7 lines of code, this is actually pretty hard, right? And it's pretty hard because this program was constructed to assign lots of different names to the same memory locations. And this is exactly what this aliasing problem is about. And in FlowDroid, for instance, which was already mentioned, we use a particular backward alias analysis that you see here in blue that actually resolves exactly these different names, right? So for instance, here where W is assigned to X.F, this would go back and uncover that X.F is the same as Z.G.F here and A.G.F here and B.F there, which is then actually leaked, right? So here you can actually have a data leak, in fact, although it's not quite that obvious to see. But any good static analyzer needs to deal with this. And I'm still seeing sometimes papers that I get for review where people cooked up some static analyzer with some quick Python script or I don't know what. And they don't even talk in a single sentence about aliasing. And that always makes me very dubious about these papers, because if you don't solve this, you're not going to get any good analysis quality. The second major challenge is related to this, but it's not identical. And it's about so-called field sensitivity. So let's look into what this is about. So let's assume we have some secret value being assigned to A.F, but then we are not printing A.F, but we're actually printing A.G. So we're printing something else, right? And there's no data leak in this code. But one could now think about representing this field A.F as something like A.star, and that is actually called a field insensitive representation, okay, because it forgets about this field suffix that you had after the A. But this would actually give you a false positive here, right? Because now the analysis assumes that A.G is also tainted, right? Because this is basically saying anything after A is tainted, so including A.G. Then we would get this false warning here. Therefore, what you actually need and want in this case is a so-called field sensitive representation, where you do keep track of these field suffixes here, right? And we also call these things here access paths. So it's basically describing a path through which a certain value can be accessed, right? And here, if you basically get a reference to A and then to its F field, then you have an access path that gives you this memory location. Now you might think, well, this is obvious, right? So why not have this in the first place? This is obviously what we want. But now I will show you an example of where field sensitivity is actually getting in your way, right? And this always, in my experience, has to do with loops or recursion and with recursive data structures. And let us take a look at this contrived example here. So this is made up, but it's actually a simplified example of a real world situation that we observed in real world code and had to deal with. So here we are assigning something to my secret to A, right? So we're tainting this. And then here we are assigning A to B.F, but also to B.G. So these two values end up being tainted here at the end of this first loop iteration. Now, when we propagate these access paths around the loop, then the following happens. So in the first iteration, we had an A here, but now in the second iteration, we have an A.F here and also a B.F, right? And now this is being assigned again here. So we're assigning A to B.F, but now because A.F is tainted, this means that also B.F.F is tainted and B.G.F is tainted and so on, right? So all of a sudden, you get this explosion here, right? So you get longer and longer access paths. And the worst thing is we can do this over and over again, right? So if we don't do anything, in fact, and if we don't bound this abstract domain that we're using here of these access paths to a finite length k, then this would not even terminate, right? So you would have an infinitely sized domain, and your static analyzer would just run forever. But even if you do bound it to some finite number, yeah, this is not a very nice solution, right? Because then you might be losing some precision. So somehow you want to have a finite representation of this, which represents all of these infinitely many excess paths that you could have. And now what we did, and also a couple of people before, like Tom Rapsey also worked on this, is we did some problem analysis, right? So in the end, what you really need here is you want to match field writes with field reads. So you basically want to make sure that when a value was stored, so a tainted value was stored to a.f.g.h, for instance, it can be read from this very same access path as well, right? So you want to match these loads or reads here against these stores. And what's interesting to note about this is that this is a so-called matching parenthesis problem. So you basically have some opening brackets or parentheses here, and you have some closing ones here. So these represent loads and these represent stores. And whenever you can match them with each other in the right order, right? So here H is the innermost one, it also needs to be here. Then this is a match. And this is something that can exactly be modeled through a so-called push-down automaton, or you might also have heard of the term stack machine. And what's nice about these is that these actually have a finite representation. So they have a finite set of internal states, and they have a stack that they operate on. But in particular, also their reachability problem is decidable. So that's a very important property because it means we can essentially compute with these things. Yet there's a third challenge that also comes into play, and that will get important in a couple of minutes. So this is so-called context sensitivity, and basically any usable static analysis that crosses procedure boundaries needs to be context sensitive to be useful. And I'll show you in an example why that is. So let's again assume we are assigning the secret value here to the string s, okay? And then it's basically assigned to this identity method. But this identity method is also called here in the second context, where the same formal argument here is assigned a different value, right? So here it's a public value that we don't care about leaking. And here it's a secret value that shouldn't be leaked. And now, if you're not careful about this, the following happens, right? So you will propagate this tainted S value here to X. And then here, if you have a context insensitive analysis, when you hit this return statement in the analyzer, it will return the tainted value to all the possible callees, not just to this first calling context, but also to the second one, which would give you actually a false warning or false positive down here, right? Because now the analyzer thinks that the secret could actually end up here at this print statement, although looking at the program, this can obviously never be the case. But now if you look at this problem here, this context sensitivity, you can actually do the same problem analysis, because here, interestingly, we also need to match two things with one another. Here we need to match method calls with method returns. So basically saying if something was passed to m of n of o, then it must return first into o, and then from n, and then from m, right? So you call method in a given order, and then they return in the exact opposite order. And this is again a matching parenthesis problem, and you can model it just as field accesses. Here we are using slightly different brackets, right, to show that it's a different variant of the same problem. But you can also model this through a push-down automaton or a stack machine. So this sounds nice, right? So we can have one push-down automaton for field sensitivity, and we can have one for context sensitivity. But there's a problem if you try to combine the two, actually. And this has to do with what you see here. Maybe some of you can guess what this actually depicts. Some of you might have seen this. So this is actually a Turing machine. built out of some, well, I don't know what it is, some toy construction blocks. And why am I showing you this? Well, it's important because that's a somewhat old already, but very important theoretical result. If you have two stacked machines, two pushdown systems, and you combine them, then you basically get a Turing machine. So it has the same expressive power. And that also means that the combination of these two is actually undecidable, right? So in particular, state reachability for a Turing machine, you cannot decide. Otherwise, you would be able to decide the halting problem, and that doesn't work. But we want to have something that is decidable, that is computable, so that we can really make a static analysis algorithm out of it. And yeah, so there was also a very formal paper about this by Tom Reps, who also showed through a different reduction that actually when you combine context sensitivity with field sensitivity, it's undecidable. So I had this explanation with the Turing machine. He basically had a different reduction here, and he showed this. And basically this gives this result that you cannot build an analysis that is fully context sensitive and fully field sensitive at the same time. It's just impossible. And this paper is already several years old, and because it existed, I guess people also stopped sort of looking into this, right? Because looking at the paper, you get the impression this can never work, right? So you don't even need to think about combining a context sensitive and a field sensitive analysis because it's just never going to work, right? But what this is essentially showing is that you cannot build an analysis that is fully context sensitive and field sensitive for every program, right? So what this is saying, give me one such analyzer that claims to have this property, and I can construct you a program on which this analyzer will fail, on which this analyzer will give you some false result, some false warning, for instance, right? Because everything else cannot be constructed. But the point is, we don't need this to work for just every program, right? And so really the main contribution of my PhD student, former PhD student, Johannes Späth, was that he showed that you can build an analysis that is fully context sensitive and field sensitive for many programs that people actually write, okay? Because there are typical programs have a certain structure to it. And yes, you can craft programs for which this will fail, but as he was able to show also empirically, at least most programs that we analyzed, we do get fully precise results. So we get very low false positive rates. And this is what came out of this Poppel paper that we published some years ago. So the paper is quite complex. I can't explain this to you in 5 minutes, but I want to show you on a very high level what the basic idea is. So if you assume that this oval here is showing all possible behavior of a given program, okay, then there's certain erroneous or vulnerable behavior that we want to detect, right? So this is what we are actually after. And typical program analysis warnings, they look like this, right? So if you take an off-the-shelf static analyzer, if it's sound, then it will tell you about all the programming errors, but it will also give you false positives here on the right-hand side, right? And some of these false positives are actually inside the possible program behavior, but some of them, they're not even within it, right? So the program couldn't even come to this program state here. And let alone would this be an erroneous state. Now, what you would actually want is such an exact match, right? Such a perfect alignment. So you want to have a static analyzer that gives you exactly this circle in the middle. But Reps and the others showed that basically no such analysis can exist, right? You can try to build this for as long as you like. You're never going to succeed. That won't work. But what we now found out is that basically the following. So if you have one pushdown system that gives you this oval here, and this could, for instance, be the pushdown system that models field sensitivity, and then you have another pushdown system like this one here that models context sensitivity, then if you don't combine them in an arbitrary way, but in some special way, and it's even though very simple, then you can get the following. So what we did is we basically took the intersection of the two languages that these two pushdown systems give us, and then you get this yellow area in the middle, right? And as you see here, that's not a perfect alignment with the red circle that I was showing, but it's close, right? So there are still false positives that we can get, but typically they are outside the program behavior. So that means we can get some false positives, but typically they're not exhibited by actual programs that people write. They can happen. And we have examples also in our paper of how you can construct a program so that they do happen. But we did some large-scale experiments and were actually unable to find any false positives that would have been caused by this approximation. And yeah, so what Sanjay also said earlier is that it's really hard to find analysis setups that are performant and have good precisions, right? And so for many years, people thought that this is basically what the trade-off looks like, right? So you have some tools that are really good in terms of performance, but they suck at precision, right? So they really give you tons of false warnings. And so here you could think of some simple free linters, right? That do some very simple syntactic analysis, and they give you some warnings, but not a lot. And they give you many false positives. And then you can have heavy-duty commercial products that probably are very expressive and precise, but you have to run them for hours, if not days, right? And this is really what the commercial landscape used to look like some 5 to 10 years ago, I would say. But what we now found, interestingly, in our experiments and also now in applying this, is the following, that this actually goes on like this. So if you keep pushing for precision, if you keep increasing precision like we did, and we were really striving for having an extremely precise setup with a really precise pointer analysis, precise call graph analysis, precise field sensitivity and so on, and context sensitivity, then the analysis, it doesn't become slower, it becomes faster actually. And here really high precision leads to better performance. And why is this? Well, this is because as the analysis becomes more precise, it can actually focus on smaller parts of the program, right? Because if you have an imprecise analysis that taints a lot and tries to basically refute a potential vulnerability in large parts of the program, because to begin with, it thinks that there could be vulnerabilities pretty much everywhere, then this costs a lot of time and a lot of performance, right? But if you have a highly precise analysis that exactly knows where the pointers are flowing, that exactly knows which methods can be called and which ones can't, then it can focus on a very small part of the actual program, even though it has a very precise analysis, right? And this can actually become very fast. And this is what all of this is about, right? So here we use basically this combination that I showed you of context and field sensitivity. And we also pair it with what we call demand-driven program analysis. So these are analyses that very quickly focus on the parts of the program that matter to the problem that you want to decide, right? So I will be showing you in a couple of minutes a crypto analyzer. And there we will quickly focus on API calls to crypto APIs. And we will disregard most of the rest of the program, right? And so we will focus on this and start a highly precise analysis from these program points. And that's really what makes this whole thing efficient. So let me talk a little bit about this crypto analyzer that we built. So this is really, yeah, you can see it as a domain-specific prototype that we built. So it's specific to the domain of crypto usages. And it's a collaborative project with some other universities and postdocs and PhD students and so on. And it has been applied by a couple of companies that you see here. And it's now also an official Eclipse project. So it's open source and you can download it, and you are also welcome to contribute to it if you have some interest in it. And basically what motivated us to build this was the following, right? So we have tons of application developers these days that have to deal with sensitive information, right? Like user accounts and payment information and sensitive documents and so on. But then in order to get this right, they need to deal with tons of cryptographic concepts, right? Like when do you actually need to use encryption and when do you need hashing? If you do encryption, what encryption mode do you need, and so on, right? And this can be very hard to grasp for several people. And in particular, not everybody had a full course on cryptography and on how to use it, right? And there are many studies, and we also wrote some of our own that showed that people frequently get this wrong, right? And so many of these studies showed that the vast majority, let's say, of Android apps or also server-side applications do misuse cryptography. And so when we built CogniCrypt, we basically had the following design goals. So first, we wanted to be able to generate secure crypto integration code. So that's part of CogniCrypt. It has one component that generates secure code for you for a new project, for instance, that needs some crypto integration. But we also wanted to efficiently and precisely detect insecure integrations that you might have already in legacy code, right? And we also wanted to be able to easily and quickly customize this to new crypto APIs. And so we came up with a new domain-specific specification language that we called CRISL, so crypto specification language, that would allow us to actually denote these analysis rules that the crypto analysis needs to check. So let me show you on just a couple of slides what these look like. So here, what you see is, first of all, the header of such a rule. So here we are saying that we are basically writing a formal specification for a class called key generator in the standard Java crypto API. And then here we basically set up our environment. So we are saying, okay, in the following, we are talking about an algorithm that is encoded as a string. We have a key size, which is an int, and then we also have a secret key. And then here we are defining some events, or you could also say method signatures, but it's better to really think of them as dynamic events. So for instance, we are saying that an event G1 happens whenever you call key generator dot get instance with a string argument. And if it gets a string argument, then this is not just some string argument, but it's actually the algorithm string, okay? And then here we can say, okay, if we write get instance in capital letters, it means either event G1 or event G2 and so on, right? And then there's another init kind of event and also a generate key event that actually returns the key that is generated by this API. And now this is just defining the environment. And then here, this is actually the second part that is defining the rules. And you can define an event order. So this is validating that you are first doing a get instance call, then potentially an init call, but then in the end, eventually a generate key call. And any other calling sequence on that API is implicitly forbidden. And then here we have API parameter constraints. So this is basically saying whenever you're calling this API that I had here, right, with these algorithm and key size parameters, they need to obey these rules, right? So for instance, if you are choosing AES as an algorithm, then the key size must be any of these three because everything else is not allowed, would be invalid. And the idea is now that you write these CRISL specification once, right? So this can be done by some API expert. Then you just give this into CogniCrypt, and CogniCrypt then basically derives from this a custom assistant, a custom code analysis, right? And you can give this code analysis then any Java application or Android application And out of this, you get a static analysis report, and very quickly so. And I just want to quickly show you in a brief video how this works. So this is actually integrated in the Eclipse IDE in this example. Here we would actually call one such API, cipher.getInstance. And if you just call this with an AES string, like I'm showing you here, this is not allowed. This is actually insecure. And Eclipse is showing you by these rules what kind of string you ought to be using here. And then you can simply go into this and correct this. And as soon as you now save the document again, and the code is being recompiled, it's also being reanalyzed, and you will see that this warning message goes away. And so it's really integrated, yeah, like a spell checker, you could say, right? So it's really very rapid. And obviously this was a very small example now where all the code is in the same procedure, and it's also a simple property to check. But this code could also be, largely apart in different classes, different packages, and it could involve these type state properties where we need to check method ordering and so on. And it would still terminate in usually milliseconds, sometimes a few seconds. And that's because we have under the hood these algorithms and data structures that I talked about. So these synchronized pushdown systems with these demand-driven algorithms. And because we now had such a precise and scalable tool, we were able to do also a large-scale empirical study using this analysis. And for instance, we ran one analysis on Maven Central. So this was back at the time about 2.7 million Java artifacts. By now, I think this has grown substantially. And then we actually found that 73% of all these artifacts, so these were mostly libraries, right? They use the JCA in an insecure manner when they use it, right? So not all of them use crypto, of course, but out of these who do, 73% of them have at least one misuse. Then we also looked at Android apps, but here we wanted to do a bit more directed study. So we looked into 250 apps and only these because we wanted to also inspect them manually. We took 250 apps out of these sectors though, because we thought here people would be security cautious, right? So we took banking apps and health and password apps. But also here we found that in 71% of the cases, these apps had at least one vulnerability, or I should say one misuse, right? A misuse doesn't always have to be an exploitable vulnerability, but I would say it's always a red flag. It's typically something that should be fixed. And we looked at some of these apps in more detail, and one of them was interesting. So this is not an identity safe password. So that's a password vault by Semantic, right? And back then it had more than 500,000 downloads in Google Play. That actually had privilege escalation vulnerability that we then also reported, and that got fixed actually pretty quickly within a couple of weeks. Interestingly, we also found a vulnerability in the VR banking app. So that's a banking app by a German bank, pretty popular as well. And what's interesting is that this was supposedly also security certified. So TÜV that you see here is a German, very well-known certification body. And I actually called them up after we had found this, because I was like, come on, this can't be right. I mean, we found really blatant crypto misuses in this app. And then they told us, yeah, we weren't really checking that part of the app. The certificate is really about some other part that has to do with how these transaction numbers are being dealt with. But of course, if you look at the web page here, they don't tell you about it, right? So they tell you it's certified and it's a good product, but it's only partially okay, really. But this was fixed as well. Yeah, so this is what I wanted to show you so far. So I think we as a community have come a long way, right? So we now have algorithms that really work very well. We have also now products being deployed that have very good and low false positive rates and scale a lot better than they used to some years ago. And that also gives us all a lot better adoption of this technology in practice. And I think that's part of this movement that you have been seeing in the last few years with DevOps and DevSecOps and so on, where people really integrate more and more of these tools into their build and deployment chains, and maybe sometimes even into their IDEs. But there's still some open challenges, right? And we are also still working towards some of these. So one really big open challenge that I see is, how can one effectively summarize the data flow effects, for instance, of library and framework code, right? So there's a lot of library and framework code out there, and many of these libraries and frameworks are used all over the place, right? And of course, we don't want to keep reanalyzing these, right? It takes a lot of time, it takes a lot of effort, and it also takes a lot of energy, right? So everybody is now talking about saving energy and saving the planet. And if we had to analyze these over and over again, that's just a waste of resources, right? And so we want to be able to summarize this once and for all so that it doesn't need to be reanalyzed. And yeah, but the challenge here is that for precision, these summaries, they must actually be able to distinguish calling contexts where necessary, right? So if you have two different calling contexts, like I showed you, that call into the same procedure, but they, their contents differ in terms of the analysis, right? So one context, for instance, is leaking something, but the other one is not. Then this must be differentiated in the summary, because if we were not to differentiate it, then we would over approximate there and you would lose precision, and we don't want this, right? So we must keep contexts apart that need to be kept apart. But on the other hand, we also want to have efficient and concise summaries, and that means these summaries must be sort of put together. They must abstract from unnecessary detail where it's possible, right? So as abstract as possible, but as concrete and differentiating as necessary. And that's really the art, finding the right trade-off there. And I currently have a couple of PhD students who are looking into this. It's anything but trivial. Then the other big question to me is also regarding libraries and frameworks, how to model these things at a scale. So this has more to do with things like implicit control flow, but also data flow through these frameworks, right? So for instance, many people now are using Spring as a web framework, but also Google Juice and so on, right? And then the question is, if you have such a framework, what is the control flow through it, right? What does a good call graph look like for an application that uses such a framework? And here you need to deal with reflection and native calls and so on. And currently, this works by people modeling these control flows by hand. So people they hard code certain rules into the static analyzer. We have done this, many other people have done this, but it doesn't scale, right? If you have many frameworks that people use, you end up doing nothing else. And that's not what people want to do. And the other big question is, what are security relevant methods? So for instance, if you use Spring, then what are relevant sources and sinks and sanitizers that are used in combination with this framework? And what are authenticators? So basically methods that authenticate users within the framework, or propagators, which are basically black holes that take a tainted value and they spit it out at some other point of the framework, right? And you somehow need to model this or recognize this as well. And this is also something we're currently looking into, but where we also haven't found the holy grail yet, right? So we have some ideas, but I have my doubts that this is really 100% solvable through technology. But I would be very happy to also hear your own input on this. Yeah, and that concludes my talk. I hope you enjoyed it. I'm very happy to take any questions and suggestions you might have. And if not now, then also after the talk. Thank you very much.